we happen to have designed the tallest building of Gujarat, which is the World Trade Center at Gift City, which is 122 meters. Of course, that's all in RCC. Today, let's focus on steel. So these are, just a few of our works. Some of them I'll be presenting right now today. A few of our industrial projects. Yeah. So let's get to the main topic. So this is actually one of our projects in Hyderabad, which is a entire steel composite structure. It has got 5 basements, 3 stills, and 16 floors, roughly about 72 meters in height. The built-up area is pretty massive. It's a 35 lakh square feet single building. And the single floor plate area itself is 1.5 lakh square feet. That's just an image. I'm not sure if the plans are too visible. I can actually open that up. Would love to actually discuss that. By any chance? Anyways, I'm not sure if this is very clear though. So the entire system, as I've mentioned in my earlier slide, it's a CFSP, concrete-filled steel tube, which is basically part of the column sections and the central core walls are the main lateral load-carrying systems. All the girders are basically designed as composite, sections with metal deck sheet and shear studs. The lateral stability, as I said, is fully provided by the central core walls. The overall footprint of this building is in excess of 150 meters by 92 meters. Important aspect of this project was that the client actually wanted to have this entire structure, as I said, 72 meters height with 5 basements, created in less than 14 months. And fortunately, the foundations and the basements have already started right now. So the challenge was, how do we actually achieve those, timelines for such a complicated structure? So again, there are of course certain important aspects that I would like to brief about this project in terms of its design. These are the codes that we've used, all the latest codes, including the Highrise code for tall buildings, which is definitely applicable in this. There are certain limitations when it comes to the Indian codes in terms of composite beam and column design. So we've actually referred to AISC 36010 and EN 1994 2004 as well for composite column design. Again, instead of conventional concrete encased steel composite columns, we've used CFSP, concrete filled steel tubes for all columns. It actually saves tremendous amount of time because it eliminates the entire rebar activity and most importantly the shuttering and the casting activity for the concrete outside the columns. Effectively what we are doing is just creating a steel box columns and filling it with concrete for all the levels. As I mentioned, 100% of the earthquake forces, that's part of our lateral system, so it's taken by shear and core walls. For the core walls, obviously the best method to go with in this case was, slip form or self-supporting jump formwork, so that it actually goes, 5 to 6 floors higher than the rest of the steel structure while it actually gets fabricated. So we have, ample of time to catch up at the higher floors. All the steel beams are designed as composite beams. using metal deck sheet of 0.1 to 0.9 to 1 mm thick with shear studs. These are the important codes that we have to comply with, along with a few international codes, a few of the seismic aspects which we obviously have to comply with. Important aspect is that which a lot of the structural engineers here might be interested in is the response reduction factor and the time period, how it was actually estimated. Since it's a shear wall building, the entire time period was estimated using that time period. The code, as I said, is all RCC, so obviously stiffness modifiers had to be duly accounted for. These are the load combinations for composite beams, for service and strain checks. Unfortunately, I do not have the video running. Would have loved to show you if how the model mass participations actually happen. This is our base model. As you can see, the central core walls right here, and rest all the spans and the grids that we used here is 11 meters by 11 meters for the columns, and then all the bays are actually spaced for the secondary beams. They are spaced at 2.8 to 2.9 meters. Again, to ensure that the optimal section for deck slab and the beams are rightly achieved. This is just a typical section of how the metal deck sheet actually was designed for. Again, an important aspect that one must understand is the minimum section for the design was 135, including the metal deck sheet. But what we've actually provided for is 150, because again the code mandates for the fire rating of 2 hours, we need to have at least 90 mm concrete topping on top of the peak of the metal deck sheet. This is just a small comparative that we had to make in order to again kind of convince the clients about why this might actually be a good option, going with a steel CFSD based system. So if you see, we did a brief comparative. So for the composite column, at the basement 4 level, the composite column size that we were actually getting and what we have actually redesigned for is 700 by 700, while the same RCC column size with an estimation of 2.5% reinforcement was coming to 1250 by 1250. If you go above, you can see the variance is pretty massive. It kind of increases the usability and the carpet area significantly for the clients as well. Another comparative that obviously we had to make and we kind of were able to get due advantage of was had these beams designed for as a composite section versus a conventional steel beam, but not as a composite section. So what actually the difference was coming? If you see, in terms of the depth of the beams itself, there was a significant change and variation in terms of depth. Just because of taking the composite action, we were able to reduce the beam sections, and as you can see, the weight of a single beam also literally halved. So the typical just connections, I'll be glad to connect with anybody to discuss on this a little more. So we actually, again, as I said, this was kind of a pioneering project for us, creating more than 70, 80 meter tall steel buildings, and here in this case, even the basements are actually all in steel. So it's not that the basements are in RCC and then from above we're actually doing steel. So we had to actually kind of convince the clients that we will be able to actually even achieve the timelines, so to say, the way we're trying to portray. So we just created a very rudimentary erection and construction sequence, assigning basic days with the labor allotment and the equipment allotment. So the first 6 months, since this is Hyderabad, as I said, and it's all rock, we effectively were getting SPCs as high as 120 ton per meter square. For excavating 4 to 5 basements, effectively we needed almost 6 months to do that activity. So while that happened, our fabrication was happening off-site. So we just did a basic analysis looking at the footprint of the building, what would be the craneage and the number of cranes and the capacity of the cranes that would be required in order to cover the entire building. And if you look at it carefully, it kind of gives you in terms of the zero date, where do we start, the crane erection and the foundation. And so on. So again, foundations effectively happen. So this is just a very brief sketch to explain them, but foundations effectively happen from 150th day to 210th day, and these are the activities that will get covered in that. From the 210th day to the 240th day, these are the activities that we will be covering. This is just an example of how 6 levels of columns are just shown as an example. Of course, that goes on above as well. Now, from the 215th day again, the secondary beam systems and the metal deck sheets till the 265th day kept on happening. In a nutshell, we kind of were able to actually get the entire duration per floor to 6.13, a theoretical number, but 7 days per floor. The total duration for the erection after completing the foundations came out to be 135 days. So in effect, this was something that we were able to very rightly suggest and project to the clients. And since this is a steel building, a lot of simultaneous activities in terms of services also happen, so that eventual deadline of 14 to 16 months seemed very plausible after this preliminary working that we actually did in consultation with 2 or 3 top contractors and steel fabricators. So that was our first project. Not sure if I covered right. So the next project I'm actually going to cover is Indian Institute of Management, Udaipur. Vastu Shilpa is the architect for this project, and we are the structural consultant. It's a greenfield project of 280 odd acres. The total development includes, the academic block, the housing, and the hostel facilities. So that, a lot of it was RCC, a lot of it was stone masonry as it is in Udaipur. We've actually done random rubble and coarse rubble masonry. I'll take you through the important steel, aspect in this project. Again, a few of our interesting structural parameters. So this is actually the library building that we did, connecting the 2 ends of the academic blocks. Not sure whether the pointer is visible, but yeah. This span was roughly about 32 meters, and there were 4 stacks of library structures, 4 floors of library that had to be accommodated. Again, erected at a height of 28 meters. So what we effectively, this is actually the floor plan, just our model that we had to make. This is how the entire floor plan looks like, and we try to use the Varandial system in this particular case to ensure all the criteria and the aesthetic and the internal functionality is duly accounted for. So yeah, again, as I said, this project is in Udaipur. This structure kind of connects 2 different cores of the academic block. So we've rested this entire structure on neoprene bearings at both the ends. One of the end is a roller joint, one of the end is a pin joint. That's our 4-storied verandials. So effectively there are 4 verandials in this particular project. One is right here on the top. So there, if you see truss elevation 1, 2, 3, 4, those are the 4 verandials that we've erected within the structure. Since the width of the structure is also in excess of 20 meters. So, just to give a general estimation in terms of the deflections that we were getting under full loading considerations was about 31 mm. This is just an analysis model for the deflection of the entire system. We actually had to undertake a lot of construction sequence process also while modeling, and ensuring that during the erection stage as well, we for erection stresses as well as the wind, we are pretty safe and in line. So actually a sequential model in terms of construction stage was also effectively made and checked. This is basically, and the same sequence was effectively submitted and given to the contractor as well for them to erect in that particular manner itself. So this is just one of the photographs of how the erection, during the erection. That's one of the ends, and the other end is somewhere here. It's all supported on the bearings. So that's the completed, structural part. The other internal photographs, again, we've used metal deck sheet and composite beams internally at all the floors. This is just another internal view where a few double heights are also created as part of the library. A view from the bottom to just get a fair idea about how the structure looks from the bottom. As you can see, the metal deck sheets. That's basically where the bearings are. Another important aspect that we had to also kind of cover in this particular case was the longevity and the long-term durability of the bearing pads. And our RCC structure should also be able to actually be designed that in case if this had to be replaced, where would the jack points be eventually. So that also has been duly accounted for, marked, and the RCC structure also has been designed for the same thing. Yeah, these are some of the on the verge of completion photographs that we have. Yeah, thank you.